By now you should be very familiar with the concept of a transfer function and block diagram algebra. So I'm going to be a little bit more explicit here about the domain in which these signals exist, so that we can be more clear about what we mean by the block diagram algebra that we're writing down. So in the continuous domain, we are used to interpreting this block diagram as having the mathematical equivalent that I'm writing down here. So in other words, we are explicitly saying that when I write a transfer function inside a block like this, the output is going to be equal to the product of the transfer function and u of s. And I find it very useful to continue to think about what a transfer function is as the coefficient of the input when we write the formula in this form of output equals coefficient times input. Now, things change a little bit when we are talking about discrete transfer functions, because often it's not clear when we can apply the Z transform or find the Z transform of a transfer function, or whether we have to calculate the Z transform of a product. Let's take a quick example. So let's imagine that we have a continuous u, which we are sampling, and we're sending that to a continuous system. I'm going to call this G2 just to avoid any confusion. If we were to sample that output, we would end up, let's call all of these 2, we would end up with y2, and we would be able to write a discrete transfer function which related y2 of z to u2 of z. And what we would write in this intervening position would be g2 of z. Now, how do we find this Z transform, which is equal to this transfer function that I've written down here? The easiest way to go about this particular problem is to consider the impulse response function of G2, and in this particular case, we simply know that we have mathematically we represent u2 of the sampled u2 as an impulse train. We'll get a set of impulse responses which are then sampled at the sampling points, and so we could simply look at the inverse Laplace transform of g of s, and that would give us g of z. Now, if this was a normal transfer function, or let's say a kind of simple transfer function like 1 over s plus 1, what would these signals look like? Now remember, I've said this before, there isn't a pulse train actually in real life, but we can think about what the mathematical consequences are of imagining that something like a unit step is changed into this pulse train, this mathematical fiction that we use when we think about the transfer function here. If we were to look at each of these signals, if I were to draw them, I would see a continuous step. I would see zeros and then impulse response, or little impulses at every time step, which are equal to the Dirac delta. And after having gone through a first order system G2, what that would look like is lots of little impulse responses. And depending on the step size, either we would go almost all the way back to 0, or in some cases, if the time step is small, we wouldn't actually have time to go all the way to 0. We would go up and down and not quite get back to 0. But after having done that, if we sample, we are back to a pulse train where the surface area of each one of these little Dirac deltas is equal to the value, the position at the position that we sampled. So that's what this would look like if we just applied the mathematical theory. Let's introduce a third transfer function into the mix now. So if we consider a new situation where we have two transfer functions in series, two continuous transfer functions in series, and we do the same thing. We have a step, we have our impulses. In this position, we have our impulse responses. At this point, the response of this new system to the impulse responses will not look like impulse responses anymore. In fact, it will look like second-order impulse responses. So in other words, it will look a lot more like this. It will be smoothed at each time point, where this one will be going immediately up, assuming here we've got, again, something very similar. Let's say we've got exactly the same kind of transfer function, two first-order filters. After the first application of that filter, we'll see impulse responses, and after the second application of the filter, we'll see second-order responses. And if we sample them, obviously we'll have different values at the sampling intervals than we had before. Now, interestingly, there's another thing that we need to consider. What happens if we were to introduce a sampling point in between these sampling points? In other words, in between these transfer functions. If I had G2 and I introduced new sampling, and then I had G3 over here. Well, in that case, unlike the previous case where I would be seeing second-order behavior over here, I would actually see, again, impulse responses. Why? Because whatever the value of this impulse response was at the sampling points, I'd be back to my impulse responses over there, and I'd be back to just the first order impulse response over here, which when I sampled it, I would get values again, but they would be the values at the sampling points for each one of these. So it's obvious that each one of these conditions is completely different. If I have a single transfer function like this, if I just have G2, I will see these impulse responses. If I have G2, if I have two transfer functions in series, I will see an impulse response at the first and then a second order response at the second. And if I have two consecutive transfer functions like this with a sampler in the middle, I will see this effect coming through and see a difference. Now what that means is I can't use the same Z transform for these two cases. So even though these are the same transfer functions, if these are G1 and G2, or G2 and G3, and these are G2 and G3, same transfer functions, but the fact that there's a sampler in the middle changes the result, and therefore it wouldn't be correct to write down the same values. Another way of thinking about this is that there isn't actually a sample signal in between these two continuous blocks, and so it would be incorrect to write down a transfer function that includes only G2 or only G3 in the discrete domain, because there isn't actually a sample signal in between. Mathematically, we would represent this rather, in my notation, we would be taking the Z transform of G2, G3 in this case, and that would relate this U to this Y. So let's call this Y alpha of Z, the sampled version of that, and let's call this Y beta of Z. In this case, that equivalent transfer function requires me to evaluate the transfer functions in series and actually calculate the product of the Laplace transforms and look that up on my table. Where in the second case, it is possible for me to calculate the relationship using the Z transform of G2 only and the Z transform of G3 only to handle each of these relationships. So you can see that in this case, in the second case, y of beta of z will be equal to g2 of z times g3 of z times u1 of z, and in this case y alpha of z will be equal to what I will call g2 g3 of z times u1, and we can see that those expressions are clearly different. So in the one case we have to calculate the z transform of the product, and in the other case we can calculate the z transforms separately.